are global ocean and wind currents, which transport thermal energy across this globe. My name is Jorge, I'm a physicist, and I want to talk about the energy associated with the ocean currents, specifically focusing on the AMOC, the Atlantic Meridional Overturning Circulation. I'm going to focus on the AMOC because it's an important driver of the climate that we have in the North Atlantic. It is bringing a lot of warm water, hence warm air, to regions of the North Atlantic, these northern latitudes that would be a lot colder without it. The energy that moves these currents is brought to us by the sun via electromagnetic radiation, which heats our planet, but also by gravity. We have tidal forces, which affect large-scale flow of water. The AMOC and all of the ocean currents are comprised of warmer surface currents and colder deep currents shown in blue here. The warmer surface currents have a lot of thermal energy and they are exchanging and depositing this energy into their local environment as they travel. So you have this warm water which is heating everything around it, moving into these northern latitudes. This produces warmer climates for all of the countries here in Great Britain, Iceland, northern United States, and Western Europe. As the warm currents travel to the northern latitudes, they encounter very cold wind and less radiant energy from the sun. This causes the water to both cool and partially freeze. This increases the salinity, hence the density, which causes it to sink. This sinking or overturning is brought to you by the relationship water has with its density, temperature, and salinity, shown in a little plot below me. Colder freshwater can sit on top of warmer saltwater. One of the features of climate change is that there's more heating at the poles than there are at the equatorial regions. This is producing more melting of ice into the ocean, and that ice is fresh water. That fresh water has a lower density. And now when we mix this cold fresh water with the cold salt water, we're left with something with less salinity, less density, so it is not able to sink as efficiently. Without this overturning, the sinking, you have taken away one of the major drivers of kinetic energy for the entire current. You'll still have currents associated with the surface that are influenced by the wind, and the wind can actually transfer some of energy below, but without this overturning, the local features associated with the AMOC will disappear, and we will not have this warmer water moving up into these northern latitudes. The simulations that forecast the effects of the AMOC collapsing are very complex. You're dealing with a very large nonlinear system that has a lot of parameters, and to be fair, we've only had a few decades of data to fix some of the free parameters in the models. But it's not extrapolation to understand the relationship between salinity, temperature, and water. And one of the consequences of cooling Great Britain, for instance, by 4 degrees Celsius is that you go from about 30% arable land to about 5% arable land. So that means